So today we're going to talk about the use of cannabidiol in drug-resistant epilepsy, but most importantly, we're going to speak about the genetics of this and how we can approach getting a better understanding of the genetics of these irretractable diseases. Many of the diseases that are impacted by this are some of the most expensive forms of epilepsy. So if we can find a genetic signature for that might predict a beneficial use or a negative response to cannabidiol, we can make a big impact with insurance companies. You'll see many of these insurance companies consider any genetic sequencing in epilepsy investigational. We believe this is a mistake on their part. There is plenty of literature suggesting the very important mutations that can change treatment options like GLUT1 and SCN1A. But nevertheless, we're focusing on cannabidiol because it is addressing the most expensive and most emotive form of epilepsy, which is with these children who suffer from SUDEP, which is sudden unexplained death from epilepsy. So on that note, you will see many companies or organizations championing the use of full exome sequencing, which we have experience with as well. In fact, this is a presentation of a family that we sequenced and presented at the International Cannabinoid Research Society in July of 2014, using panels combined with exomes. And the rest of this presentation is going to demonstrate why we believe you need both. So, for one thing, you will see several people in the epilepsy field suggesting that the hunt for new genes in epilepsy is coming to a close. And I don't think by any means INGO means this is completely over, but the rate at which we're discovering new genes related to epilepsy is decreasing, which is a good thing, and that list is getting close to 500 genes. So in many ways, we can in fact narrow the selection of genes that we sequence if we believe that's going to be more congruent with the concerns of insurance companies. Insurance companies are concerned about false positives in exomes. They're concerned about follow-up testing costs that they may lead to, and so they're very much not interested in paying for investigational discovery projects. They're out hunting for these new genes. Now, I think the other debate that we're going to go over today is that these exomes tend to produce a false sense of finality, that you have sequenced everything in the genome, and that's just fundamentally not true. And in fact, there are sacrifices that you pay when you move from panels to exomes, which is why if money was not an object, we would perform both. Okay, in absence of being able to perform both, we would recommend you start with a panel, because the panels cover all of these genes that are known to be in epilepsy, and they cover them very deeply. We use the same technology whether it's a panel or an exome. It's just a question of the economics of performing 20-fold the amount of sequencing work to look at these other genes. And the cost of performing sequencing outside of the published genes certainly raises some flags with insurance companies, but also what we're going to show you today is that it makes you lose clinical sensitivity on the most published genes related to epilepsy. The variant discovery process is very simple. It's in the cloud today. That's really not the challenge anymore. The real challenge is discerning which variants are benign and pathogenic. And it's our belief that the best way to do this today is to get the best minds around it, and those best minds are often distributed throughout the world. But with modern technologies like Skype, we can readily tie all of these people together and bring the best genetic counselors to bear on every single patient. And that's our approach. And the reason for this is that computer algorithms today really do a poor job connecting phenotype to genotype without clinical context being interpreted by specialists. So we believe in that type of bench strength. Now let's go into publications we're seeing currently with the use of with the use of exomes. You'll see some whole exomes here in mitochondrial disease, and they're only presenting 88.6% of the bases being covered more than 20-fold. Okay. Why 20-fold is an important number, we'll see in a slide in just a moment, but keep this into context. This is 11 bases out of 100 that are under 20x. That's one undersampled base every 9 bases. That is by no means an A in genetics, it's an F. Now, there have been papers that have come forward and challenged this approach, saying, hey, look, you can perform panels in a much faster turnaround time for about a third of the cost and have the same diagnostic yield. And that's in fact very much what we see. We believe this concept of diagnostic yield is a very subjective definition. It is very dependent upon the population in which you're sequencing. Many of the pathogenic variants are graduated in clinical review based on their frequency in the population, and that population has really only been measured with 1000 G and the ESP6500. Both of those databases are ethnically biased. They tend to consist of lots of Northern Europeans, and they have very little sequence coverage in the Middle Eastern populations and the Southern Pacific populations. So variants that might be quite common in those populations will look rare in Northern Europeans and sometimes get falsely called as a putative variant. So this diagnostic yield we think is a dangerous number because of all of this subjectivity, and we actually believe we should get buried in and anchor things in clinical sensitivity from a sequencing standpoint. Knowing your sensitivity and specificity, those are more important numbers than diagnostic yield. So why do we care about coverage? Well, if you sample a base only 10 times, you have a 90% likelihood of being able to detect a heterozygous base. And that's because 10% of the time, you will sample that heterozygous base as an 80-20 allele ratio, and your computer programs will have a hard time calling that a homozygous or heterozygous base. So pushing it up to 20-fold coverage narrows this gap. It's an asymptotic gap, but nevertheless, 20x seems to do a good job with single nucleotide variants. You will see some exomes in the field here. This is one from GeneDx, where they are measuring things on 10x coverage. This is a sign that they are cutting corners. 58x mean coverage is a very light exome and by no means has diagnostic sensitivity. But where this really shows a dramatic difference in performance isn't really with these single nucleotide variants. It's actually with insertions and deletions, because these types of lesions in the genome require far deeper coverage to actually detect. Okay, so here's some papers that show that 21% of the variants in the human genome are in fact insertions and deletions. And since they're not single bases and they consist of multiple bases, they actually consist of as many bases that are varied in the human genome as single nucleotide variants. And they're often more pathogenic. Okay, so this is really the most important class of variants to be able to clinically detect. And what we're going to show you is that people taking these 58x exomes are cutting this corner, and it's very irresponsible because it is missing the largest class of variation that is responsible for clinical manifestation. So here we have, again, exomes being trumpeted in the New England Journal of Medicine, and some of the exomes that they're pointing to in here have 92% coverage. That's 92% of the targets are covered at least 20 times. And what we're going to show you is that might be adequate for covering SNPs, but it is poorly adequate or inadequate for covering these insertions and deletions. So 1 in 12 bases missing is another way of thinking about 8 bases out of 100 that are undersampled, but the 500 gene panels can push this up to 98%. Now, the other number we have there, which is 67% and 85%, is derived from us looking at what we call truth sets from Genomes in a Bottle. This is a National Institute of Standards and Technology project that sequences certain genomes, like 12878, with every platform they can get their hands on to come up with the distilled truth set of the variations in that genome. So we take that genome and we sequence it with both their panels and with their exomes, and we go about measuring our sensitivity and specificity at different coverages. And you can see an exome here with the SNPs at 85x and 101x up here in the top part of this chart, and the sensitivity and specificities aren't very different from what you'll see from our panels, which we'll show you in just a moment in the next slide. But when you go into the indels and you start playing around with long reads, and you look at sensitivity and specificity at 85x, you can see we have only 67% sensitivity. We can double the coverage up to 181x and move that to 73%. We can try 2 different base calling tools to call them and improve it a little bit more. We can try 3 callers and get the numbers up to 80%. But if you take a look at what some of our competitors are doing, like GeneDx, they're doing single-ended 50 base pair reads. This is giving them the benefit of the doubt that they're using paired-end 50 base pair reads. and their sensitivity plummets to 57%, okay? So the take-home message here is that you need read length to call indels, and many of the competitors doing these exomes are cutting corners by using short reads. They're doing that to get faster turnaround time, but it's coming at a cost of indel sensitivity. Not very apparent in the SNPs, however. So on the right here, what you see is a graph of indel size, and this is a log scale graph. So, 10,000, 1,000, 100, 10, 1 on this axis over here, counting the frequency of indels in the clinical databases, ClinVar, and graphing them and bidding them according to their size. And what has been conventionally difficult to pick up with people using these 50 base pair reads is this bracketed clinical blind spot. 50 base pair reads will not pick up 10 base pair indels. You'll see that disclaimered in GeneDx's reports. In fact, they won't even call heterozygous variants that are 5 bases. In size. So lots of limitations on what they can detect. Now, this log count shows you how much more important this region is, and then picking up what MLPA might pick up out here at 200 bases. Okay, MLPA and exon CGH have sensitivities out here. They can't pick up any of the small stuff, but paired 250 base pair reads can. So comparing this to some of our panels that we have in the next slide, you'll see our epi panels push the coverage numbers up to 400x, and it improves our C20s and our C10s, but more importantly, what we look at for indels are our C100s. How many bases do we have covered 100 times? Because we believe we really need that much coverage in order to pick these up, and you can see those numbers are north of 90%. Again, we have taken this approach and applied it onto this genomes in a bottle that you'll see on this next slide. It's published here by Justin Zook. And if you take this 12878 genome and sequence an entire exome only up to 80x, you can count the number of indels that you missed because they know where they all are. So we count those up and you can see, all right, we have close to 100 indels under 50 bases that we have failed to detect in this genome. If you double the coverage, or more than double the coverage, up to 181x, these numbers of false negatives plummet in half. We believe if you move this all the way up to 400x, which we're doing currently, these numbers will come down again. And it's a very coverage-sensitive metric here. So why is this important? Well, sometimes our competitors are pushing 2 different tests. They're selling this exon CGH to pick up these 169 base pair lesions, so out here in this area that's very low frequency, as a separate test on top of their very cheap sequencing, where they have done 50 base pair reads and cut every responsible corner known to man, and they're picking up these, and then they're selling you a separate test to pick up these. What we're demonstrating by sequencing these genomes in a bottle is that we're picking up all the way out to these 50 base pair ones, and with our sequencing alone, and if you just add up all of these columns, we have far more clinical sensitivity than performing a test that picks up some of these and some of these. So the net story here is a famous line from Indiana Jones: they're digging in the wrong place, and they're bilking customers by charging them twice for this type of sequencing sensitivity, meanwhile pointing out that we have limited deletion and duplication detection, so it's kind of ironic. Now, the other challenge that we see that comes along with exome sequencing is that there's only so much clinical interpretation power out there. There's 3,000 genetic counselors in the country, and so when you hand them 40-fold more variants, what tends to happen is each variant has less attention paid to it by a human. This is a little bit worrisome today, particularly if the variants have nothing to do with pediatric care, like BRCA1 or ApoE. So here's an example of a report from an exome from a competitor. I believe this is also GeneDx. And all that's listed on there is one single variant, and that's it. Now, we try to deliver this type of brevity in our reports, but we also link in extended reports that give an in-depth amount of hyperlinked data on all the other genes that we believe are involved in that could be putatively involved in the disease pathway. Now, none of these are necessarily going to be labeled as pathogenic like the one here, but they are variants of unknown significance that might be of interest to the physician. So we really believe in providing this because we are in a real exponential moment of discovery where next week, LAMA2 may become the next gene that is thought to be linked to a particular disease state, and they'll want to know if this was a rare variant or whether it was a completely common variant and whether it has any play in their patient. So we're believing in providing this type of information. It can be quite a bit if you are to do that with an exome. So we have been trying to focus the panels on all the genes that have literature to support their role in the disease pathology and thoroughly report on all of those. So now with this, we're applying this type of approach where we comprehensively sequence 500 genes known to be in epilepsy to 400x coverage with these long reads, so we have indel detection. We're including a handful of cannabinoid pathway genes because we believe this pathway may play a role in the response rate, and we're taking a very close look at P450 genes. Why we're doing this is because many people with exome sequencing get drowned in so many variants that they frequently will filter them all out based on population frequency. So any variants that are common in the population will disappear from the reports. Well, that happens to be and describe most of the variants in the P450 genes that dictate drug metabolism. They are common, and they will get filtered out of many exome reports if you're not careful. And so we believe in pulling those forward because they have a real important role in understanding how to deploy CBD, and we also believe they will have some role in the response rate. So there are two trials ongoing. There are multiple IRBs involved in this, working with UCSF, NYU Langone, Elizabeth Thiel at MGH. We also have Seattle Children's involved, and CHOP down in Philadelphia, where we're trying to coordinate this to understand response and non-response in the patients that are being given Epidiolex, which is a form of plant-derived CBD. The Denver Health IRB is looking at a different derivative of CBD. It's still from a plant, but a different plant that may have different background cannabinoids and different background terpenes, and that's a plant called Charlotte's Web. And so we're sequencing in that population as well to see if there's any difference that can be detected. Now, onto the P450s. This is it's well known from Watanabe's work that cannabidiol has a potent inhibitor of P450 3A4, 3A5, and 2C19. And the pathway for CBD is over here on the right, and it shows you the different metabolic routes and which enzymes they go through to be metabolized. And those happen to be the same enzymes that are required to manage some of the anti-epileptic drugs out there, like clobazam and steripental. Both of these go through the 3A4 pathway. And so with our sequencing, we like to provide our physicians with reports like this, which show every contraindication in terms of drug metabolism with one drug versus another. So you can see up here on this upper axis, we can see cannabidiol and its impact on the metabolism of a variety of other anti-epileptic drugs, and then likewise every other anti-epileptic drug's impact on CBD is listed in this column. So this is important to know because we have seen some cases of patients that when they go on cannabidiol, the clobazam levels seem to go up dramatically, and that's something that we want to keep a close eye on. You can see here it's in des-methylclobazam is what they're seeing. This is actually a prodrug that gets metabolized, and so that's something that we'd like to keep our eye on, particularly if they happen to be a slow metabolizer in the 2C19 family or the 3A4 family. Right here, this patient has normal metabolism, but if any one of these were slow and it combined, they were on clobazam and on CBD, we would be concerned that they may have a drug-drug interaction that goes on. We also like to put these into tables that might highlight these as consider alternatives or use with caution, just so it summarizes this type of complexity into something that can be easily digested. So all of these patients go through our pipeline. We have a variety of collaborators here helping with this, from translational software, looking at the P450s, to simulconsult, doing phenotype-genotype connection, and then seizure diaries in here for some of the patients to try and track their seizure frequencies as they're going through this project. And Ingenuity is a tool that we are using to stratify these patients in the end. It's not a patient-by-patient tool yet. It's something that just looks at collections and cohorts and tries to use a tool that will segregate responders from non-responders by looking at the genetic data. So we already have some data in. NYU and CHOP both have their IRBs approved, and 8 patients and 9 patients respectively have come through and been sequenced. Denver Health has 3 consented to date. Their IRBs also approved. And then MGH and UCSF are quickly going to follow. And some of the variants that are coming out of these patients are beginning to show up, and we can see the typical SCN1A variants. Lots of calcium channel genes and lots of potassium channel genes that are involved in calcium. So the signature of there being some mutagenic burden in the calcium channels is already showing itself. But again, we think we'll need 100 or 200 patients here to really get to any conclusions on response. So with that said, we'd like to summarize here that exomes are a great discovery tool, but there are some shortcomings that need to be understood. No AI database, we think, can today replace the professional interpretations of 2014, and we've got to be very careful about this circular reference that goes on. People putting pathogenic variants into databases because of computer algorithms, and everyone else self-referencing those pathogenicities into future discoveries. This is something that is still creating a lot of consternation in the field, and we try to put the best brains on top of that to resolve those things. So thank you for the time, and we'll end it at that.